Live on the YouTube. All right, guys, I'm going to wait a few minutes if you're hearing me right now. I'm doubtful you guys are or whatever. I'm going to go ahead and wait a few minutes if you'll get a chance to get in before I actually start lecturing. Later today, when everything goes to YouTube, I will timestamp when the lecture actually starts. So if you're watching this after I actually streamed it, just look in the comments or something and I'll put the timestamp for when I actually start lecturing. We are going to do some electrolytes today. Continuing lecture from last time. If you're hearing me, I would like for you guys to actually get into Discord and actually get into the general chat channel. So if you guys have questions, you can actually ask. If you're able to ask questions, it'd be awesome. All right, I'm thinking a minute or two, I'll get started talking. Hello. Hey guys, I'm gonna start lecturing soon. If you haven't gotten to my the YouTube live stream yet, I'm getting ready to start. You guys see me all right? Still gonna wait a few minutes to start. Just wanted to talk a little bit and figured give you my face while I talk. So yeah, you guys shouldn't be going outside right now. It's crazy out there right now. We also got a virus going around. You guys all know about that. My nephew went out to grab lunch earlier, and he was telling me how crazy it is with people out there right now. And he was looking in their cars and stuff to see like who they were bringing with them. And you have people out there with their kids too. Like honestly, like this is not vacation time, guys. This is stay-at-home time. We need to actually keep this virus under control. And if we are actually, you know, massing more than usual, it's literally going against what we're supposed to be doing. Hello, Brianna? I think I heard you talk. Did someone say something? Don't know. Anyway, please stay at home, guys. This is not vacation time. Stay home. You should have got your shopping done earlier. I mean, but you know, if you have to go out, you have to go out. But yeah, you don't bring your family. Just go yourself. Yeah, my nephew's staying with me right now. Honestly, he doesn't normally stay here, but he's staying here now to help me watch my son. I have a 6-year-old. He may join the video. We'll see if he will stay upstairs the whole time or not. All right, I'm seeing a lot of people that are in the class in the comments. Hey, Brianna, I'm going to mute you because, can you hear me? Brianna? I'm going to mute you. Yeah, turn on your push to talk, please. Join the voice channel, the general. Oh, I should be touching my face, right? Oh, I can't remember that. Look at that. Okay. Yeah, we just detected our house too, so I'm not worried about being secure, and I've not left the house today. I've been at home playing on the computer, figuring this stuff out. Alright guys, hey, if you guys are watching this, but you're not, please join the general voice chat channel if you want to engage with the lecture. This will be a much better experience if you guys actually ask me questions. We can pretend like we're in the classroom. You know, just, I think it'll be a lot better rather than just watching it like a YouTube video. I'm trying to make this as close to a experience as possible to what you would get in the classroom, but yeah, we have to deal. So, but I'm trying to make the best of the situation. But yeah, I'm thinking one more minute, I'll start for real. So let me switch it back over to this thing. For real. So back over to the back. I'm just not going to afford paying that every day. Time like this? Here to feed you guys. Yeah. Okay. Yeah, I'm going to start talking about chemistry with you guys. So this is the cool. One good thing that's now is for us is that I'm sort of yeah. You know, full yeah. But right now they're going to be like, you know, wanting me to work overtime. After I use the shift here to my one is on in Charleston, it's $9 an hour to site. So I was just mad. I don't want to say, hey, if you can give me a 3 days somewhere else, I'm just going to be we can't pay for that. Yeah, that's all right. For what I'm doing. All right, I'm going to start. All right. I'll see you later. Once I get on. Alright guys, if you haven't done so yet, if you're going to be in the chat, you need to please turn on your push to talk, because I can hear someone's phone right now. And yelling too, so I'm going to mute the person. Alright, so getting started here.
It's by your name on the bottom.
Okay. Yeah, I was actually going to show how to do that real quick. So let me switch over. Oops. And desktop capture. Let me pull this up. All right. So pardon the windows. I'm showing you the desktop here. So. Yeah, so your options for your voice settings, if you're on a computer, it's right here, and on your phone, it should be next to your name somewhere. There's a cogwheel. So you click on the cogwheel, and then right inside here, there's app settings. You want to go ahead and click on voice and video. And then in voice and video, there's an option for push to talk. And you will, if you're on PC, you'll set your button. I think there's actually a button for it on phone. And you also have an option to check if your mic is working, if you actually want to engage. So, yeah. And if I'm getting a bunch of random sounds from you because you didn't push talk, I will be muting you because it can't be distracting me while I'm trying to teach. So, all right. So, but I did hear someone talk just a minute ago. Do you want to talk again, please? Someone said something earlier. I don't know. All right. Well, anyway, I'm going to go ahead and get started into the lecture. We're going to be picking up about halfway through the PowerPoint. Hopefully you guys have had you guys have Canvas available. You should have the PowerPoint already. And I'm going to be going back and forth. Like you see the different camera setups here right now. I'll have a display where it full screens the PowerPoint, and then I'll have my little face in the corner, and then I also have like a document camera setup where I'll basically be writing on paper. So that'd be like my whiteboard talking that I would normally do in class. So, and then these are actually the topics I'm going through today. So I'm going to give you a little brief introduction into equilibrium. I want to revisit weak electrolytes. We talked about those, like weak, medium, strong electrolytes last time. I wanted to revisit with the weak ones. We're going to go over what equivalence means, and the big part of today's discussion is going to be over concentrations and dilutions. And here's where the math is at. So I recommend that for today's lecture that you have a calculator handy if you want to follow along with calculations. I actually need to grab my calculator. Hang on. Right here. I got it. Calculator. And you also need a periodic table for these calculations. We're going to be doing like gram-mole conversions. We did them previously, so hopefully you guys did not forget how to do your gram-mole conversions. I'm hoping that we have enough time to do osmosis also. It's an applied topic here, and we'll see. We'll see how it goes. So with that in mind, I'm going to go ahead and switch over to the document camera, and I'm going to start talking to you about equilibrium. I'm going to... Yeah, I'm not sure if this Discord thing is going to work, but I really want you guys to have the option to engage with me. I just needed another person because I heard myself talking through their mic. So, all right. So here, and then you also want to give me be patient with me. I'm still learning the software. I kind of fumble a little bit because I'm not a regular game streamer or something like that on my weekends. All right. So here, let me fix that, and I'm almost ready to start talking. All right, so last time we did talk about weak and strong electrolytes. Remember, strong electrolytes are things that will fully ionize in solution, and then you have your weak electrolytes, which only kind of partially ionize. You then have your non-electrolytes. These are things that are typically soluble in water, but they do not ionize. And we say they're non-electrolytes because of the fact that if they do not ionize, they do not conduct electricity. So only the weak and the strong ones do conduct electricity. All right. So we did talk about, once again, the strong ones are the ones that fully ionize. I'm going to skip through a little bit of this here, and then come talk about this one. Hey, watch out for the cat. Yeah, so my cat might interrupt the video too, so we'll see. All right, so here we have an example of weak electrolytes. We're going to be going over acid-base chemistry. That's kind of what this topic will segue into. But I did want to talk a little bit about how these reactions work and help you guys understand what equilibria actually is. So I'm going to go ahead and switch over to the document camera view, and I'm going to work with the carboxylic acid example that's up here. All right, so for my example here, I'm going to go ahead and use acetic acid, which is HC2H3O2. And I'm going to show you both the shorthand version, and I'm actually going to show you we actually draw it out as an organic structure and how this kind of works. So this way, notice the way I'm drawing the reaction arrow. I'm using a two-way arrow. This means that the reaction is actively going both directions. And you can kind of think of it as like a scale. You have two different weights on a scale. Let me see. There we go. Two different weights on a scale, and then one side gets heavy, the other side goes up, and vice versa. This kind of thing happens in chemical reactions. So what happens here is that this can break apart into your H+, and then your acetate ion. And it's starting out neutral, and if you lost an H+, in order for it to be overall neutral on this side, that means that the acetate ion has to have a -1. The kind of functional groups that do this in organic chemistry is the carboxylic acid functional group. That's why we call them that. And let me just go ahead and draw out the structure for this, and we can see the functional groups involved. So here I have, remember we call this the COOH, and this is how we draw it out. And it turns out this is our acidic, the actual H in the compound that is being acidic. So the H's over here are not leaving. It's actually the H that's from the oxygen. And we have the equilibrium arrow. and then H3C, C, O, and then it's O minus now because it lost that H.
I have a question.
Oh, sorry, go ahead. Go ahead. Somebody had a question?
Is this only weak electrons? Weak electrolytes?
Yeah, so the main difference between weak and strong electrolytes is that basically whether or not you have an equilibrium error or not. So if you have a strong electrolyte, it's fully on the product side, and then if it's a weak electrolyte, you have a little bit of both reactants and products around. So yeah, so typically the concept of equilibria that I'm going to be building up to here is only with weak electrolytes. If that. You don't have to circle the charges here. This is the organic chemist to me doing that. So typically you do want to circle your charges. In organic chemistry, so they kind of stand out, but you don't have to. It's not that big of a deal in this course.
Okay, thank you.
Okay. All right. We do have a way that we express this mathematically, and they call it the K equilibrium expression. If you take Chemistry 122, which is like the second semester freshman chemistry course, you guys really deep dive into this stuff. But for this class, I want you guys just to kind of understand, like, if you see something numerically, which side of the reaction is favored. We're not going to do any of like those crazy quadratic equations that go along with this that they do in Gen Chem. So for a generic reaction, if we have a reaction that is going, say, A plus B is an equilibrium with C plus D. The way you write the equilibrium expression is you say that KEQ, so it's capital K, and then EQ is for equilibrium. This is equal to, the general form is products over reactants. So, and these symbols here mean concentration, and I'll write this stuff out here too as we go along. So, C, D over A, B. So remember here on this side, on the top portion here, we have products. And then on the bottom portion here, we have the reactants. All right, so if you think about it here, if imagine that, if this reaction favors, say, the product side, like the product side just has a natural tendency to be heavier, you have more C and D than you do A and B. What ends up happening mathematically with the KQ equation is that the top portion of this ends up being larger than the bottom. So we say that KQ is large, or basically it's greater than 1. So I'm going to go ahead and write this out. So if you have a situation where KEQ is greater than 1, that means that the products are favored. So you still do have equilibrium, it just means that the side that has the products is the naturally favored side. So products favored. It's going to work out for a lot of our weak electrolytes. If you actually were to look up their K values, there's a natural tendency for a lot of these weak acids to have a favor towards the reactant side, meaning they're less than 1. So yeah, that's the next example here. Is KQ less than 1. This means that the left side of the equation is heavier, meaning reactants are favored. Just remembering offhand, the K value for the reaction I just showed you guys is on the order by 10 to the minus 5. That is, definitely less than 1. So that means that in the real world out there, if you were to look at a mixture that had acetic acid in it, most of it's intact still. And then the other part is where it's ionized. And it's the ionized portion that's actually making it an electrolyte. It's not this part. So like, for example, if this part, soluble in water did not ionize, it would be a non-electrolyte. But because it's kind of partially ionizing, it makes it a weak electrolyte. Are there any questions about that before I continue? Give it a second. I know there's a little bit of a delay between like real time and what YouTube is seeing. So, all right. So let's go ahead and continue.
What do you mean by products and reactants favored?
It means which side of the reaction is dominating. So when these things go in solution and they're in equilibria, a reaction does happen. If it ionizes, It's basically the degree on how far it goes. Like, did it fully ionize, did it partially ionize, that kind of thing. So, for example, if you were to look up the for strong electrolytes, if you were to look up the K values for the strong electrolytes, you'll see that the products are very largely favored, and so they'll end up being very large values, meaning that they're greater than 1, and then the product side is favored. This is important because we're going to see next chapter also that we can do things chemically to make it shift towards one side or the other to kind of get things favored, and biology does this all the time to kind of tweak things to what it wants. So I'll go ahead and oops. All right, so just keep this in the back of your mind. I just wanted to give a little bit of introduction on equilibrium. We're going to kind of deep dive into this more in next chapter, but I just wanted to kind of mention it here. This is how we kind of mathematically talk about whether it's strong or weak. All right, the next thing I'm going to go back to the PowerPoint now, and then unless there are any more questions, you guys may throw your questions out there if you have any. I wanted to look at equivalence next. I got to find the slide for it. Give me 1 second. All right, this one. I want to look at this one. All right, so we have the concept of equivalence. Equivalence, I like to think of it as how many of the thing of interest are being delivered per mole. It typically corresponds to how many plus charges or minus charges it's bringing along. So I'm looking at the third bullet point where it says 1 mole of sodium ions has 1 equivalent of charge because the charge is +1. So yeah, so if you had, say, 1 mole of sodium ions, you kind of have 1 mole of plus charges. And then, for example, the next example there is 1 mole of Ca2+. That generates 2 equivalents of charge per 1 mole of the calcium ion. So it works out where equivalence is basically equal to the charge on it, at least when you're working with the plus and minus charges. Yeah, so the very last bullet point there, remember once again, the number of equivalents present per mole of an ion is equal to the charge on the ion. And next what we're going to go over, how to calculate molarity and how we go to normality with that, which is basically equivalence, how we use that. All right, so I just want to go ahead and switch to the doc cam. I just want to go ahead and show you guys how to do molarity and just do it on paper. All right. So this concept is called, we're looking at concentration now. So when you think of concentration when looking at different solutions, it's basically how much of the solute is in the solvent. So once again, it is how much solute per solvent. So there are some common ways that these are expressed. In chemistry, we like to use a thing called molarity. We often use things like grams per liter. So what I want to go ahead and do here is this PowerPoint does go through all the different forms, and I just want to go ahead and use one solution and kind of go through all the different ways we can calculate concentration with it. All right, so imagine here that we have, let's say, 150 grams of sodium chloride, table salt. So NaCl. And then let's say this is in some water. So let's say that is in, I don't know, to make up numbers here, guys. Let's go with 750 ml of H2O solution. I like to use the shorthand SOLN, that means solution. A solution is a mixture of solute and solvent. So just, it's everything all mixed together. We call it a solution. All right, so the first thing I can do here, a common one that people will see is grams per liter is a very common one that people like to calculate. So all we need to do here, so most of these typically, let me just back up a second here. These are typically in the form of some kind of mass per volume. It's very, very common that this is done. Or you can also think of it as solute over solution. That's another way to think about it. Anyway, I'm getting kind of sidetracked here. All right, so we have 150 grams of NaCl. And then all we're going to do here is I'm just going to simply divide it by how many liters we have here. So if I have 750 mLs, you guys should know how to calculate how many liters you have without too much difficulty. This should work out to be, so if we move the decimal over 3 spots here, we end up with 0.75 liter. So I'm going to write this as 0.750 liter. And then that's our setup. This one's done. So all we have to do now is punch it into the calculator. So let me go ahead and pull this up. Oops, kind of dark with the lighting there. Let's see. So I'm just going to go ahead and say 150 divided by 0.75. And then I'm getting exactly 200 for this. Yeah, 200. All right, so it's 200. Put a decimal there for 3 sig figs. And then the units here are grams per liter, like so. All right, so that's for grams per liter. That's not quite molarity yet. So the way we define molarity now is we're going to have to put how many moles of it do you have per volume of per liter of solution. So you're, typically, if you have a problem like this, if you're calculating molarity, you're going to have to convert grams to moles. So we're going to need the periodic table for this next part. So let me go ahead and get some definitions written out here for you. So we are going to be looking at molarity. We will symbolize this as a capital M. That's actually the unit for molarity, the capital M. And this is moles of solute over liter of solution. And I'm being really particular on the wording here, so I'm saying liters of solution, not liters of solvent. And the reason why I'm wording it that way is because if you actually take 150 grams of NaCl, like you have the powder, and then suppose you have like a beaker that has the water in it, and you mix them together, it's not actually exactly 750 milliliters. You actually get a little increase in volume due to the mass of the NaCl that you added in. So the liter of solution is accounting for that additional volume. So typically what people will do is, like when they're making these solutions, they'll actually add the solid and then add enough water until it goes up to 750. They won't actually measure that separately then mix, because that doesn't work out to be correct. So let me go ahead and show you the setup here to do this calculation. So we start with 150 grams of NaCl. And I'm going to have to do a little side calculation on, I need the molecular weight for NaCl. So I'll show my work down here. We have enough room for this. Yep, there we go. So in the formula we have 1 sodium and we have 1 chlorine. So you just basically, remember, you look up their masses on the periodic table and then you're going to add them all together essentially. So sodium is about 23. I'm going to round for this just for the sake of brevity, making it a little bit shorter. But yeah, it's 23 grams per mole roughly. And then this one is 35.45 grams per mole. So then if I add this together, what is that? 0.45, 50, like 58 something? Yep. So 58.45 grams of NaCl, and that is per 1 mole of it. Like that. So what that's going to do, it's going to give us the mole part on the top on this equation here. And then now to finish the problem, all you have to do is just go ahead and take your volume, which we used up here, and then divide. So I'm just going to put it down here just to tell myself that I'm dividing by this in my calculator. And then if you think about it here, the grams cancel out. So let me cancel it. So the grams cancel out like that, and then you're left with mole over liter, which is what we want. So at this point, we have our setup all done. We can go ahead and calculate our time. So it was 150 divided by 58.45, divide 0.75, and final answer is 3.42, whatever 3 sig figs we can use in this class. And I'm not being too particular about sig figs with you guys, so just 3 is enough usually. And there we go. 3.42 M. You could have also written this as 3.42 moles of NaCl per liter. That's basically what it's saying if you have just the capital M. All right, so I think the best thing to do here is maybe do another example, just make sure you guys are okay with this, and then I'll start showing you the other types of calculations that or the other types of concentrations that you may run across. All right, so let's go ahead and say that we have, let's say we're looking at sugar in blood or something, like a sugar blood concentration. They typically do that, I forgot to do that in, blood's usually done in deciliters, but let's do a molarity thing. So let's go ahead and say that we have 320 grams of glucose. And then I wouldn't expect you guys to just remember all the different formulas for the different sugars, but this is a C6H12O6. You may have heard that from your biology classes before, but I would provide the formulas for you guys because you need them for calculations. So 320 grams of glucose in, let's say this is in 5.23 deciliter. Actually, let's just do liter. Hang on, fix that. Just do liter. Keep it simple for now. Liter. And then I want to calculate, and then the way we symbolize concentration, writing out the symbols, you can say concentration of C6H12O6. If you see someone writing these brackets like that, that oftentimes will mean concentration. That's actually why I put that in the K calculation earlier. So brackets, that means concentration in molarity. Concentration in molarity. All right, for any of these problems, if you're starting with grams, you have to have the molecular weight here. So that's definitely a side calculation you do at the start of the problem. So the way we're going to do this here, and I'm going to round here a little bit. You guys should, if you're doing your homework, I recommend using exact values, but I just want to show you the general setup here. So if you look at the weight of carbon on the periodic table, it's about 12. So it's 6 times 12. And then we have 12 hydrogens. So, oops, sorry, keep bumping the camera. All right, let me fix that. 12 times H. That one. The weight of hydrogen is about 1. So I'm going to go ahead and say it's 12 times 1. And then we have 6 oxygens. So that's 6 times 16. Yeah, the weight of oxygen is about 16. That, and we just need to calculate all this out, and then add them all together. I usually type it in as a string. I personally, when I do problems, I don't actually write this out anymore. And by the time you get done in practice, you shouldn't have to either. So 6 times 12 plus 12 plus 6 times 16, 180. So our molecular weight is 180 grams per mole. Like that. To go from grams to mole, you divide by this number. So if you're given grams to start out with, you're always going to divide as your first step. So I'm going to go ahead and do our setup here now. So I said 320 grams of our C6H12O6. My line there, and then we're going to divide by 180 grams of the C6H12O6. That is how many we have per 1 mole of it. Like that. And then the very last, so at this point, just like the last problem here, the grams drop out. We have moles now. And then to get to molarity, you need to divide by how much volume you had, which early in the problem we said it was 5.23 liter. And that has to be liter. Like that, and then now we have our setup. Just punch it in your calculator, you're done. All right, so 320 divide 180 divide 5.23, and I am getting a 0.34 for that one. Equals 0.340 capital M per molarity. All right. Are there any questions about how to do molarity from grams? I heard a sneeze. Okay, so I want to go ahead and do another problem, but then I want to kind of go into normality. It's how we talk about equivalence. All right, so suppose we say we have something like, let's say, 130 grams of calcium chloride. There's a couple things that we can go with these kind of problems, but let's just go ahead and say that it is in, and let's just go ahead and make up some numbers here, 872 milliliter. Yeah, oftentimes these problems are typically given to you in ml or liter, so we just got to work with it. All right, so just like before, the first step here is typically calculate moles, and you need to get the molecular weight. There was that little app that I showed you guys before. I'm actually going to use it here just to illustrate again how to use it. So I'm grabbing my phone. I'm going to show you guys how to do this. All right, so the app that I used before was the EMD periodic table. That stands for periodic table of elements. And then it's free in any of those different mobile stores. All right. So here's your periodic table, and then molar mass calculator. You want to it has a sample one in there for you to look at how to type it in, but you just type it in as you read it. So we said calcium chloride, this one, and then done, and then it's calculating the molecular weight for me, and it also gives you elemental composition in this particular app. So I'm just going to go ahead and read that number. You should know how to do this without the app, though. However, so it's just if you're doing a bunch of problems like this saves you quite a bit of time in doing problems, because this is almost always the first step that you have to do. All right, so I'm only going to take it to moles right now, and then I'm going to talk about a couple of different things that we can do with this. So we can go to moles just by simply dividing by that number that my app gave me. So it's grams of calcium chloride per 1 mole of it, like that. And let's just go ahead and calculate this one out, and then I'm going to show you guys a couple other things that we can do. So 130 divided by 110.984. All right, so I am getting a 1.17. The units right now are mole of this stuff. So 1.17 mole of calcium chloride. All right. So at this point, we can go to things like. Sorry, let me mute my phone, guys. You should do that for class. I gotta do it when I'm at home, also, I guess. All right, so at this point, after you have it in moles, you can go to things like concentration that we have here. We can basically, at this point, I can divide by this in liter to get molarity. So we can go ahead and do that one real quick. So the concentration of calcium chloride, remember these brackets being concentration in molarity. We can take our 1.17 mole, divide by the volume in liters. I moved the decimal because we're in liters now. And then we have 1.17, show that up better, 1.17 divide 0.872, and my calculator is telling me 1.34 for that. And the units now are moles per liter or just capital M. Yeah, but it's mole per liter. Some other thing I can ask you guys to do here would be how many equivalents are there of calcium in there. I could also ask you guys what is the concentration of the chloride ions now. So let's do the chloride ion ones first, and we'll see how this works out. So what I'm saying now here is I want to calculate the individual concentration for the chloride ion. So calcium chloride should ionize in water. And so what I have here is, I'm going to go ahead and start off with the 1.34 that we got for our last problem. You also could have did it where you started from here, but you have to include this number in your calculation somewhere. But anyway, I have moles of calcium chloride. And then now what we can do is we can make a mole relationship for basically calcium chloride to chloride. And so I call this a mole ratio. So we need to figure out how many moles of chloride we have per mole of the whole thing. And then from the formula, we can see that there are 2 chlorines per the whole thing. So the ratio here is 2 to 1. And if you think about it here, this is moles per liter. The moles of calcium chloride cancel out, and then you end up with moles of chlorine over liter now. So this works out to be this concentration of chloride. So just take your 1.34 from the last calculation times 2, which is that, and then I end up with a 2.68 for that. If someone were to ask you, say, hey, what is the calculation of calcium ions now, or Ca2+? Oops, let me slide this up just a little bit like that. It's going to work out where the calcium concentration is actually the same as this one. And it's because the reason why it's going to work out to be the same is because for one of the entire thing, you get 1 mole of calcium ions. You could write it out, but the ratio would be 1 to 1. But yeah, let's go ahead and do it for the sake of discussion. So 1.34 moles of calcium chloride, and then that's per liter. And then we know that we have 1 mole of calcium ions per 1 mole of the calcium chloride. So yeah, so you see how we're just multiplying by 1? So it works out to be 1.34 molar for that one. All right. Another thing you might be asked here too is calculate what's called the normality. Normality is actually equivalents per liter. So I'm going to show you first how to go from moles to equivalents, and then from there you can go to normality. So I'm going to go ahead and set up here. So let me just start a new page actually. It's probably easier. So normality is the symbol N, capital N instead of M for this. And this is equivalents per liter. My son's being yelled at for running upstairs right now. Tristan, stop being bad. Alright, so back to what we're doing here. So in order to do this here, you have to calculate the equivalents first. So we're going to keep just continuing with that calcium problem. And so I'm just going to write the numbers down here that we had. So we had calcium concentration was the 1.34 that we're going to use. So I want to go for normality of calcium 2+, figure this out. So we know that the molarity is 1.34 moles of calcium 2+ per liter. And then remember that the equivalence number is equal to whatever the charge is. So it's going to work out here where we get 2 equivalents of the calcium per 1 mole of the calcium ion. And that, remember, it's just equal to the charge. So we say we have 2 equivalents, I'm going to put equiv for short, of the calcium 2+ per 1 mole of the calcium 2+. And then we already have the liter here, so moles cancel, we have equivalent per liter. So this is actually going to be the same answer as the chloride ion. It usually works out, if you actually calculate the normality of both ions involved, they typically work out to have the same normality. That's actually a way you can check your answer. Alright, so it's 1.68. I'm going to grab my calculator, or 2.68. I don't know what I'm going to grab my calculator for. Alright, so 2.68 units normality, and people will often tack on exactly what you're talking about, so it's normality of the calcium after that one. Alright, so are there any questions about molarity and normality? Give a second for people to ask if they have any questions. right. All right, there is this section that's in your PowerPoint slide. It's definitely, you know, a lot of you guys are trying to go to nursing school, and a lot of the stuff that I'm going over right now is actually part of the language of being in the hospital, to be honest. So a lot of times when they're talking about like your blood levels and stuff, and like how much you have in there, like they're going to be a concentration unit that they're using. So one of the really common units used is actually milli equivalents per liter. Here on this chart here, we have all the different cations and anions. These are like, you know, their average concentrations in blood plasma. So sodium ions, calcium ions, you know, potassium ions, that kind of thing. And notice the units there. It says MEQ. That is milli equivalent. So it's milli normal. So I would write that unit out. The one here, I mean, right here, that I would put that as little m, capital N. That's basically what that is. So that, because that EQ liter is the capital N. All right, so the next one here. Yeah, so this is giving you a lot of extra information. This is not a biology course. I mean, yeah, it's definitely relevant for you guys. So I like presenting the information, and if you actually have interest in, you know, working as a nurse, this should be like, this is pretty interesting, let's check this out, kind of thing. But I'm not testing you on a slide like this because, yeah, we have enough stuff that I'm forcing you to memorize. So this is just like an FYI slide for you guys. All right, so I want to take a look at other types of concentrations real quick, and I kind of want to get through everything today, and then we'll probably do some actual practice next lecture. So you need some time to absorb it all, and I actually want you to try some practice over the weekend. All right, but the next one I want to take a look at is percent concentration. This is one that's very common as well. Percent concentration can be reported in a couple different ways. The most common ways are like mass per mass, or simply weight per weight. You can also do volume per volume, and then also really commonly is mass per volume is very commonly done. So for this particular example here, we're seeing on the page here where it's percent mass by mass. You just take your grams of solute and then divide it by the grams of solution, and then you have to multiply it by 100% to get it to a percentage. If you have just the first part where it's just gram over gram, that's I call it the ratio, and you're not quite percent yet. You need to multiply it by 100 to get 100%. But look at the units there. The units are gram over gram, so the grams cancel, and the unit that's left over is percentage. It's the same thing for volume per volume. Slide change, there we go. So volume per volume is just, you know, a volume over volume. Here this example is giving you an ml over ml, but as long as they match, they cancel. So yeah, as long as they match in the volume per volume, they work. And then we have percent mass per volume, very common. That's actually kind of how we're talking about molarity, because that's a mole, which is the mass, over our liters, which is volume. And often in chemistry, we have this here, percent. All right. We are going to work in going through how to go between different units. I'm going to just reserve that for next time for practice problems, but I'll show you guys how to go between the different units. It is a little bit of a process. But the last thing I want to talk about before I move on to dilutions is ppm and ppb. So if things are really low concentrations, it makes a lot of sense to report them as a ppm, which is a part per million, meaning you have like 1 part per 1 million, and then there's parts per billion, where you have one of these per 1 billion of the solution. These are very small concentrations, and they work out where there is I'm mousing over here. It works out that ppm is equivalent to milligram per liter. So if you calculate a milligram per liter, you also did calculate the ppm. And I believe, yeah, ppb is microgram, which is 10 to the minus 6 grams per 1 liter. And I will make sure I include some ppm, ppb stuff when we do the practice the next time. All right, so next thing I want to take a look at here is dilutions, and see what the slide is for. I like to do, you know, I'm like using the paper, but let's see what this PowerPoint has. Yeah, whatever. I'm just gonna draw it out. Talking about orange juice. All right, let's just switch over to the presenter camera. So The next thing we're taking a look at is dilutions. So we have dilutions. So essentially what a dilution is you have something that's more concentrated and you're typically adding more of the solvent to make it more dilute, meaning you have less mass per volume. It's typically how this works out. Really commonly done calculation because things typically come in concentrated and we make them more dilute to be kind of usable in a lot of cases. All right, so let's just go ahead and just do like an analogy here and see how we can think about it. So suppose here we have like a bucket of water. So let's say here that we have 1 liter of H2O, like that. And suppose also in the bucket, dissolved in the bucket, you had, let's just go ahead and make up some random numbers here. So 200 grams of NaCl dissolved. So this one is your solute, that's your solvent. So then imagine that someone took the same exact bucket. So this is just after they did this here, and they added enough water, so you had 2 liters of water now. So 2 liters of H2O. The question I have now is, did the amount of salt change when the person added water to it? And you're probably thinking, well, no, duh. They added water, not salt, and that is exactly right. We still have 200 grams of NaCl in there, unless more salt was added, of course. But if you're just adding the solvent, the amount of the solute is unchanged. However, it changes in the math though with how the concentration works, because we now actually have doubled the volume of solvent. So that's going to affect our calculation for our concentrations here. And so the general term that we think here is like, so from one to the next, we know that the amount of solute did not change. So let's do a few things here before I get the actual equation with the box around it for you. So we know that we have molarity. Molarity is moles per liter. It works out where if you know the molarity of something and the volume, you can actually calculate moles pretty easily just by multiplying them. So it works out where if you have molarity times volume in liter, it works out where this is equal to mole. Like that. So if we call this condition 1 and condition 2, so 1 and 2, it turns out that we have an equation here, and I learned this as M1V1. I think your book shows it as C1V1. It's the same thing. So I'm going to show you the way your book shows it to you. So your book shows it as C1V1 is equal to C2V2. C is concentration, B is volume. And this is true because you are not adding any more solute. So if you actually think about it, multiply both sides out, you're going to have whatever mass of the solute you had. But the volume's different. So I want to go ahead and do a practice here where I calculate the concentration of this, and then we use this equation to get the concentration of this one. And we're just going to go ahead and assume that it's 1 liter of solution on these. So 1 liter of solution, 2 liters of solution on these. And here's the equation that needs the box. That's the takeaway equation here. Alright, so using this here, so we know that we have 200 grams of NaCl, and what I'm calculating right now is I am calculating the sodium chloride concentration for the first part. I might have to move my face to somewhere else on here. Let me move my face up to the top. Whoop. Whoa! Alright, sorry to be a silly here. Alright, so 200 grams of, NaCl of 1 is equal to, we calculated the molecular weight earlier of NaCl, I believe it was 58.45. So it's 58.45. And it's per 1 mole. It's grams on the bottom. Like that. And then to get to molarity, all you're going to have to divide by 1 because we have 1 liter of solution. I remember that was the thing we're saying here with that. We're going to assume that these volumes are the solution volume. So 1 liter of solution. Alright, and you guys know, I'm gonna keep saying all semester long, do your setup, then get the calculator. Always set up first. Did someone ask a question? I thought I heard something. Go ahead if you have a question. I don't know. So I'm not sure if that's someone's TV or if I'm actually hearing a question. I'm going to mute you. I'm sorry. But all right, so I did during that I calculated this to be this was 3.42 I got for this. So yeah, 3.42. I took the 200 divided by 58.45, and then you're dividing by 1, which is 3.42 m. All right, for the next one, I want to go ahead and calculate it the way that we're doing it here, and then I also want to try it with the new equation that we got. And then I want to go ahead and do one more practice problem with just using this equation. All right, nose is itchy. All right, so the longhand way here. So let's calculate the NaCl concentration of the second one. Let's pull this up a little bit. All right, this is for the second one. The amount of salt did not change, so it's still 200 grams. They added just water. And then we are going to divide by the same molecular weight. It's the same compound, so it makes sense. So 1 mole NaCl. And then we have 2 liters now because this is the second condition. So 2 liters of solution. So it's going to be this divided by 2 basically. But let's just do the whole thing out. So 200 divide 58.45. I am getting the same number, and then divide 2, and then yep, it's half of that. So if you think about it, if you double the volume, you're halving the concentration. That's how it's going to work out here, and that's called a dilution factor. But yeah, I'm getting ahead of myself here. This is 1.71 molar. All right. So what I'm going to do now is I'm going to take the same numbers and I'm going to use this equation and show you guys that if you do it this way or this way, it's going to be mathematically equivalent. You get the same exact answer. So, so what we were saying here was that condition 1, so M1 was 3.42 molar. The starting volume, V1, was 1 liter. We're going to calculate what is M2 after the dilution. And then we know that V2 was 2 liter. All right, so I'm going to use you can use M's or C's here, doesn't matter. It's just letters. They're used the same way. Okay, so here this actually looks just like we saw under the Boyle's law stuff. The algebra is identical. So instead of having a P there, we have a C instead. Yeah, same way. So I'm going to solve for M2. All right, I'm going to C's now. Yeah, like I said, I was taught with M's, but your book's using C's, so I got to mix it up. All right, C2 is V1, V2, C1, like that. You're going to end up a lot of time in these calculations where you have a V over V. That right there is your dilution factor. So you guys probably heard things like diluting things in your everyday lives, like, oh, add 1 part to this to 5 parts that. That's basically this is what you're talking about. So this is called a dilution factor. Dilution factor. It should work out because we're doubling. We're going from 1 liter to 2 liter. Our dilution factor should be 1 to 2, or yeah, half. So plugging in here, V1 was 1 liter, V2 was 2 liters, and then times that by our initial concentration of 3.42 m. Like that, and then just multiply it out. So I still have the number from earlier. We actually did that earlier, so the same exact calculation. So we have 3.42 divided by 2, and that worked out to be 1.71 and then molar, like that. Same answer, same way. They're kind of mathematically doing the same thing here, but you need to be okay doing it both ways. So whether you calculate the concentration from grams to molarity, or if I give you a starting concentration, if we would do a dilution, how do we do this? So let's go ahead and just do one more dilution problem, and then we'll move on to some stuff. I think I'm going to go for another maybe 10-20 minutes, and then I'm going to keep these videos about 80-minute lectures, because I think 2-hour lecture is kind of ridiculous. That's why we do the breaks in class. That's why we do group work, that kind of stuff. But yeah, we're just doing videos, so bummer. I like the group work, guys. That's actually how I get to like talk to you guys and get to know you guys, is during that part of the class. All right, so let's go ahead, and I'm going to make up a problem here. I'm going to move my smiling face over to this corner again. Woo! All right, move down. All right, so suppose you're working, you're working as a student worker in the lab, and you have to make a solution of sulfuric acid. So typically, when we order acids from the store company, they come in bottles that are concentrated. So question I'm going to propose is, how would you make a 0.1 molar solution of sulfuric acid from 18 molar sulfuric acid? So how would you make 0.1 molar H2SO4 from 18 molar H2SO4? So yeah, this would be the concentrated stuff that we order, from the chemical supply company, and this is like what we actually use to work with. And it works out that people don't typically buy these pre-made, because you actually save a lot of the cost if you make it yourself. And it isn't that hard, honestly. But the thing, you have to know how to do some math to do this. All right, so I'm going to go ahead and you typically need to know how much you're going to make to determine how much you need to work with. So I'm going to add a little blurb in here. Suppose a student worker needed to make 2.5 liters of it, like that. All right, so if you think about it here, we know how much we need to make. So we need this concentration, we need this volume of it, and we know we're starting with this. So essentially, what you need to know is, how much do you grab from this bottle when you're making the stock. So the way we set it up is our M1B1, M2B2, or C1B1, C2B2, however you want to work it out. Since you're actually starting from this one, I like to call this, wherever you're starting from, I call it the ones. So I'm going to call this one C1. That is our C1. We're trying to make C2. And then this is B2. We need to know what is B1. How much of that stock do we need to dilute this? All right, so I'm going to go ahead and set up my equation. We saw that it was C1B1 equal to C2B2. And then we're going to go ahead and do a little bit of algebra, just like we did during Boyle's Law. And I'm going to solve for B1. So B1 is equal to, looks like it's going to be C2 over C1 times B2, like that. All right, and then after we have our setup done, we now plug in our numbers. Then after all that, that's when I grab my calculator, right? So be careful on the plugging in part. Mistakes can be made here. So 0.1 on the top, molar. Units have to match to make them cancel. 18 molar on the bottom, like so. And then we multiply this by our 2.5. And just so we're all clear here, this is going to tell you how much of the stock you need to prepare the solution. So I'm going to go ahead and take my 0.1 divided by 18, which is this part. I got 0.005 repeating, and then times 2.5. All right, so you got to be careful here in units. So I'm going to go ahead and just give us 3 sig figs just for the sake of discussion, but that's 0.0139. And my units there are liters. So the M's cancel. My unit is liter. So I have to have liter here. All right, so that's a pretty small volume. Think about it. Typically in the lab, you'd probably measure that in milliliter. It's about 14 milliliter. To keep our numbers the same, I'm going to go ahead and say it's 13.9 ml. So the way I would answer this question now is you want to take 13.9 milliliters of 18 molar H2SO4 and dilute to 2.5 liters with water. And if someone were to do this, they would prepare a solution of our 0.1 molar H2SO4, and they would have that much of it. They'd have 2.5 liters of it. I know a lot of you guys are going to be going on to nursing. They work with IV bags. A lot of times this is the kind of calculation that go on behind the scenes when they're figuring out how to make those bags. So they have to know how much medicine goes in there, how much saline solution goes in there, and honestly, even when they're making the saline solution, they need to know how much of the electrolytes go in there. Because if you guys don't know, saline solutions are basically electrolyte solutions. They're basically like flavorless Gatorade, essentially, and without the sugar, of course. That they pump into your blood. And they all typically will mix in the medicine in there into a saline solution also. So so that's how you do that particular problem. All right. So I think I'll also make up some dilution problems to work on with next time. So next time is going to be a lot of practice problems before I actually start into the new chapter. I do want to take a look at this in a little bit more detail just to kind of give you kind of an idea of what's coming next chapter. So one thing you guys could do would be to, if someone asked you, what is the acid concentration of the solution that we made? So I'm going to go ahead and say, what is the H plus concentration of our 0.1 molar solution? So what is the H plus concentration of 0.1 molar H2SO4 solution? All right, so these are the kind we were doing earlier today. So I like to write this out as mole over liter, just so we're really clear on the units. This is technically a compound unit, meaning it's more than one unit together. So when you're working with compound units, you typically want to write out what they actually are. So this is 0.1 mole of H2SO4 over 1 liter of solution. All right, and then we can now use a mole ratio to go between moles of H2SO4 to moles of H+. So we want moles of H+ to stay, like so. And then we have moles of H2SO4. And then you typically figure these out from looking at the formula. So we're looking at sulfuric acid here. There are 2 hydrogens in there. So the ratio is going to be 2 to 1. 2 moles of H plus per 1 mole of the sulfuric acid. So so this is just going to be 0.2. So 0.2 molar is our final answer for that. What we're going to be doing next chapter is we're going to be basically deep diving into acid-base chemistry. And for anybody who knows even a little bit about acid chemistry knows that pH is important. pH is basically how we talk about exactly this in more, I like to think of it like more layman terms, even though it's used a ton throughout chemistry as well. So pH has the definition. So pH is equal to, and here we have a new function we haven't seen at all in this class yet, is the log function. It's negative log of the H plus concentration, and it has to be in molarity. So negative log of H plus. So if you have a graphing calculator, or sorry, any kind of scientific calculator, you have a log key on there somewhere. You need to find every calculator is different. And then I should have brought home more than one calculator, but some calculators are kind of weird about how you use the log key. So what I mean by that, some calculators want you to type in the number first, then press the log key, and then someone should press the log key, then the number. So you have to figure out what your calculator wants. My calculator that I've been using for demos, it wants me to put log, then number. But if you have a calculator that has a single line of text on it, like a simple, like $5 or whatever, simple scientific calculator, it's not graphing, a lot of those want you to put number, then press log button. So yeah, just check out your calculator, and I'm giving you a heads up now to check out before Monday. So that way you're ready for Monday's lecture. All right, so mine is alpha L, alpha O. Yeah, so my calculator is weird. It actually doesn't have a log key on it. But it has alpha command. If I type out the word log, it works. So log and then parenthesis. So if your calculator has a log button on it, it'll actually just type that out for you automatically. And then I want the number in there, 0.2 that we got. And then it's going to be a negative number there, right? But remember, we have a negative sign there. Negative times negative is positive. So typically you're gonna get positive values for your pHs. If you punch in your calculator without punching the negative first, it'll give you a negative answer, and then the negative that's in the equation basically makes it positive. So our actual pH of the solution here, let's do it to 2 sig figs, would be what, 0.70. All right, that's our pH. So essentially the way pH works, it allows it, the reason why we use the log scale is because log scales are very, very broad, and because we're using a logarithm scale, it allows us to basically express a really large range of numbers really conveniently. So basically it takes these huge numbers that are in scientific notation and then makes them easily readable numbers like this, 0.7. This isn't the best example here, but we're definitely going to see when we have things like 5 times 10 to the 3, converting that to a logarithm scale actually makes the number really easily readable versus having it in scientific notation. But I'm getting ahead of myself here. This is the pH chapter, next chapter. Make sure you know your log button's out on your calculator. All right, the last thing I want to talk about before I end the stream today is osmosis. So this is actually the same exact discussion you guys have in your, I think they go over in Bible 89. I'm pretty sure they do. But osmosis. I want to look at this picture right here to talk about it. And oops, I forgot to switch it over. There we go. So osmosis and diffusion. So it turns out that if you have in order for osmosis to occur, we have to have what's called a semi-permeable membrane. I'll actually write a few things out here too on paper, but I just want to kind of talk for now. You have a semi-permeable membrane where only certain things can pass through it. And what will end up happening in these semi-permeable membranes is that things like water can kind of freely go back and forth. And what will end up happening is, imagine you have like one side of this membrane has like high NaCl concentration, and the other side has kind of low concentration. What ends up kind of happening if there's nothing stopping it, they tend to kind of even out a little bit. And the net result is that water tends to flow towards the side that is more concentrated. This example here is, I do want you guys to remember these words, even though they're technically biology things. I do like to ask questions about them. You have situations where the blood or the solution in the cell and the concentration outside the cell are different, and the cell actually responds to it in different ways. So in the case where the solutions are equal to each other, we have a situation that's called isotonic, meaning that there is flow going back and forth, but there's no tendency to kind of fill one side more than the other because they're already equal, so they're going to kind of stay equal. Next we have the hypotonic solution. We're looking at the middle one right now. This is the case where the concentration inside the cell is greater than outside the cell. So what ends up happening is water pushes into the cell to kind of ease the gradient there, and the cell ends up expanding because of it. It's getting more water inside of it. And then the other case here is where it's hypertonic. It's where the concentration outside the cell is less than inside the cell, and so water will flow out of the cell, causing the cell to kind of shrink up. So so once again here we have the different terms for the solution: isotonic, hypotonic, hypertonic, and we just talked about what those were. And the words below here are what we say what the cell is doing. So normal cells, we have hemolysis or hemolysis. So it's basically like blood splitting. You can think of it. Remember, lysis means split. So if you think about the cell could eventually burst if it gets too much water in it. That's the kind of way I thought about it when learning this stuff the first time. The lysis means, it's going to pop when it gets too much water in it. And then crenation is where the cell's kind of shriveling up and getting smaller because of the concentration difference. All right, so let me just go ahead and put it on paper here, just so we're clear on the flow and where things are going, and so you guys are understanding how this is working out. So switch over to the presenter camera. Boom, boom. All right. So in between them, remember we have, this is the key feature here. We have a semi-permeable membrane. I do want to mention that these are not only found in cells. Chances are, if you have a reverse osmosis system in your house, giving you, nice filtered water, nice to drink. Remember, the water out of your sink is still drinkable. You don't have to go to Albertsons and bombard them for looking for bottled water right now. Your water out of your sink is technically drinkable right now, at least for now. But anyway, semi-permeable membranes, I have a hard time saying that word, allows water to kind of flow, but it doesn't allow the solute to flow, at least readily. So imagine here that we have a high NaCl. It could be anything for that matter, but we typically use electrolytes for our examples. So NaCl is an electrolyte. And suppose on this side we have a low NaCl. The direction of the flow is going to, remember, it's going to flow towards more concentrated. It's basically going to kind of equal out the concentration. So the flow goes this way, like that. It turns out there actually is a physical pressure we can measure. You're pushing something in there. The pressure that's going in there, that's referred to as osmotic pressure. So osmotic pressure. All right, and there is an equation for this. I'm just going to show it to you guys, but I don't think I'm going to calculate what that. I just want to show you that there is an equation for it. It's actually, we use the symbol pi for osmosis, and it's equal to the molarity times the R gas constant. That was actually the R that kind of just showed you guys the ideal gas law, and then it's times temperature. Temperature does have an effect here. So yeah, it's pi is equal to MRT, and like I said, there's going to be any calculations with this. I just wanted to kind of show you, hey, there is some math for this stuff. People did. All right. The last thing I want to just quickly mention here for lecture content is you guys have probably heard about things like reverse osmosis. And if you think about it, if you want clean water to drink, you want it to have a low concentration, right? So if you think about the flow naturally flows towards the high side, which means that this concentration is going to go up because it's losing volume. So there's a natural tendency to become more concentrated on this side, less concentrated on this side. The way that reverse osmosis works, it basically pushes against it, and the water goes towards the more pure side. So if you apply the pressure to it, you end up having a system where you're generating cleaner water than what you started with. So that's the short version, the very short version on how reverse osmosis works, but it's pushing against the gradient to get it to go towards the less concentrated side, and it's reversing the order of it. That's why it's referred to as reverse osmosis, because we're making it do the opposite of what it's supposed to be doing. To get nice clean water in your home, I recommend you should have things like a nice drinkable water at your home. You should have a water softener at the minimum. That removes magnesium, calcium, that nasty stuff from the water. It's bad for your kidneys. Talked about if you have too much of it, it can give you kidney stones. And then you also should have a filter on it. Filters are really good for removing organics. So it turns out organics get into the water from the environment. Also, living in a metropolitan, we end up with pharmaceuticals in our water supply just because people flush meds down the toilet. And also, if you actually just, take a med and then urinate, you're going to be putting meds in the water that way too. So it's not because someone's being stupid, it's because you're in a metropolitan area, there's people here, meds are going around, they end up in the water. This is how it is. Can't avoid it. But if you have a filter that catches that stuff, and usually the water district's catching that stuff too, they have filters for the water too, you should catch it again at your house just to make sure that none of it's getting to your mouth, just to be safe. Alright, so that's technically the end of our lecture. I just wanted to switch over to the face cam and just kind of chat for a second about what's going on. So let me switch over to face cam. Let me mute this thing, desktop capture, and this does not need to be here anymore. Alright guys, so I'm asking for you guys to please give me feedback on how this was today. This is actually my second time doing this. My first time was this morning. I did it for my Chemistry 103 class. I have no idea how this kind of feels from your perspective, so I would like for some feedback. So you message me on Canvas, whatever, say I liked it, I hated it, do this better, whatever, this is annoying. But I really want your feedback. I want you guys to have a great experience with this stuff, because I know this is kind of a crappy situation. I just want to make sure that you are making the best out of it possibly can. So please give me feedback. I'm also asking for you guys, moving on, that you guys go ahead and get Discord going, because if you guys can talk to me and engage the class, I think it can feel like a classroom. I really think this has potential to feel like a classroom. So, but you're seeing my living room in the background instead, right? Anyway, I wanted to also reemphasize the point about stay home. It is not safe to go outside right now. People are being crazy. And the whole point of the cancellations is to prevent spread of viruses right now. So if people are massing out there freaking out over Albertsons, it is defeating the purpose of why I'm teaching you from home. Yeah, so please stay home. If you have to go, please leave your children at home if you can. If someone there to watch them, keep your kids safe, keep the elderly safe. They are the most prone to the sickness. And yeah, and if you're going out there, repeatedly, you might get it and bring it home to them. So yeah, so staying at home is the best option now. But if you have to leave, you have to go to work, you have to go to the grocery store, I think gas stations are open still. There's actually a list out there. I don't have it right now on me, but yeah, there is a list out there what is still open. But from what I understand, the short version is that grocery stores are open, gas stations are open, and then automotive places are open, hospitals obviously are open, and stuff like that. But yeah, if you look it up. But yeah, please stay home. And on that note, I will see you guys on Monday. We are now officially done with this chapter. If there's any little thing that I didn't talk about, it's not going to be on the quiz. And I'm hoping to get quiz content and stuff like that kind of rolling out as we go through the week, but nothing will be due till next week anyway. So focus now on content. So work on problems, read the book, watch other videos, whatever you do to study. Start doing that now for this chapter, chapter 8, and then kind of read into chapter 9. Alright, I will see you guys on Monday. And then remember, pop in Discord or whatever for questions, email me, talk to me if you need any help. Alright, have a good one, guys. Be safe.